Hello class, I hope everyone is well. This is explainer video number 1 for the second semester of organic chemistry. So the question that I was given was to watch a video by this Australian chemist talk about the structure of insecticides. And I was given two chemicals to analyze, dieldrin and chlorodane, and to identify the starting materials and determine if they are exo or endo Diels-Alder reactions. Before I just go into the nitty-gritty details of the mechanisms, I thought the history behind it was really interesting. So to talk about these chemicals, first we have to talk about the original insecticide, which is DDT. And during World War I and World War II, there was a lot of people dying and germs, and another big problem with that was there was a lot of bugs, so they created DDT to help kill as many of those pesky insects and mosquitoes that spread all the diseases and stuff. But it turns out that that chemical was way too persistent in the environment, and would be handed on to further generations through like breast milk feeding and other stuff. So they decided to try a couple other ones, and one of the chemicals of study was dieldrin. It was an alternative to DDT, but was also found to be persistent in the environment and was even more toxic to humans than DDT, and was phased out in the 1980s. Chlorodane also similarly was supposed to replace DDT, but was extremely persistent and was bad for the environment and phased out in the 1980s. So if anything is to be learned here, I think humans are just too good at chemistry. Okay, first let's start with the dieldrin reaction. So here, let me put this in focus because otherwise you can't see anything. Okay, cool. So this is the original structure that was given in the video. Figuring out how to get this to 3 reactants was kind of tricky, but the question hints at looking back at the last term for epoxide and alkene reactions. So I added some extra double bonds and then used peroxy acid and chlorine, which we'll talk about later, which I hope is what the explainer question was getting at. So anyway, if we break this down and we look for where potentially the new bonds were formed in the Diels-Alder, we can see hexane rings formed here. So at first, this second ring kind of gave me some trouble, but I ended up deciding that a bicycloheptadiene could potentially work here with a cyclopentadiene with a bunch of chlorine sticking out. So as we can see here on the inside is where that is going to get pushed up to create that bicyclo nature. So I guess the final molecule is tricyclo if we're ignoring the epoxide ring. So I drew the first reaction here, and I drew the first part roadkill so that you could more easily see the transition states and where my mind was going for the stereochemistry. So as we can see that initial bicyclo ring is getting pushed downward, with the diene on the leftmost side not participating in the reaction, which becomes important for the MCPBA reaction. And with the dashed lines here, I drew this transition state where the bonds are forming, where they're breaking, and then we can see that Cl with the the colored in wedge coming out from the page. So then we get this molecule that is almost like the original, but we still have that extra alkene bond over here. And if we just use MCPBA, or honestly we could use any peroxy acid here, we get that final epoxide ring here at the end. So the reactants that I have listed, and I don't know if I did the IUPAC names right, but I think I'm pretty close. We have bicyclo 3,4-hepta-2,5-diene, hexachloro 1,3-cyclopentadiene, and MCPBA, which again, that could be really any peroxy acid. And then after I go over the next one, I'll describe why this reaction was endo. The next one we have is chlorodane. The reaction that was given, or the compound was drawn like this in the video, but I ended up drawing it like this for my own sanity so I could visualize it a little bit better. But this drawing is important when we come back and talk about if it's exo or endo. But for now, I just drew it like this for my own sanity. Alright, so this one has a little more easier reactants. And again, I drew in an extra alkene that's not necessarily needed for the Diels-Alder part. However, to get 3 reactants using a sort of alkene addition mechanism made it easier to imagine 3 reactants. So, again, here we have that kind of inside chlorine that's going to get pushed up. It's a bit more simple than the previous one. So again, I have the dashed lines to show the transition state right here, where the bonds are forming and breaking, pushing that chlorine tip towards the top, and then we still have that unused alkene bond. So then over here we have the molecule with the alkene bond that we can then chlorinate to get those 2 chlorines at the end, similar to up here. So the reactants, this one was a bit easier on the IUPAC naming. The cyclopenta 1,3-diene, hexachloro 1,3-cyclopentadiene, which was used in the previous one, and chlorine. And now, to finish this video off, I'm going to talk about why both of these reactions are endo. So the videos that I watched and from the textbook, an easy way of identifying an exo and endo reaction is to visualize what is being pointed into the page and what is coming towards me. If this hexane group, or bicyclohexane or heptane group, would be pointing upwards and out of the page, it could be described as exo. So if we were to draw the 2 implicit hydrogens here, both are coming out of the meaning that the heptabicycloepoxide thing is pointing downwards, meaning that it is a endo reaction, which is often more favorable and happens more often in nature. And there's something else I was going to say, but I forgot. So if we look at the chlorodane as well, whoops, we get here, again, we can see that the cyclopentane is pointed down and the implicit hydrogens are pointing up. Oh, I remember what I was going to say. At first, the cyclo nature of the substituents kind of threw me off. But if you think of them, if it's just one large substituent, or you think about these 2 pointing as separate, they're still the main substituents, and the hydrogens are pointing outwards from the page, and so the substituents are still pointing downwards, making the reaction endo and probably more thermodynamically favorable. And these reactions also occur because we can see that the transition states are aromatic, making both these reactions thermodynamically favorable. All right, that was a lot. Thanks for listening, and I hope everyone has a great night and that this video was helpful.